Okay, so we're going to look at the 29 paper 1 for AQA AS chemistry. We're going to look at obviously what the correct answers were, but also we might consider about how you might have approached particular questions or things to think about for similar questions in the future. Okay, so starting with the first question, the question asks us, says sodium fluoride contains sodium ions, Na+, and fluoride ions F-, Na+ and F- have the same electron configuration. Explain why a fluoride ion is larger than a sodium ion. So we're told that they've got the same electron configuration. So we have to think about what's different about them. And it is asking us to refer really why the fluoride ion is larger. So we're going to phrase our answer in that sense. So they have the same electron configuration, but what they do have that's different is they have a different number of protons. So one of the things that we should say then is the fact that it has fewer protons, and we could even say it has 2 fewer protons. And then what's the consequence of that? And one of the things that we need to make sure that or if we're thinking about the words, appropriate words to use, I noticed that some students use this to refer to pulling. So they say it doesn't pull in so strongly. We've got to get more precise in our language. So the whole point about protons and electrons, or the whole issue with them in chemistry, or the whole thing that we have to consider, in chemistry, is the fact that they are opposite charges, and so we get an electrostatic attraction. So electrostatic attraction is a really, really important concept in chemistry, and what we're doing is we're comparing the relative electrostatic attraction between the nucleus and the outer electrons in sodium and fluoride ions. So if it has fewer protons but the same number of electrons, then what we've got is a weaker electrostatic attraction with the outer electrons. And so please try always to, if you use the word forces, make sure you include attraction. If you use the word electrostatic, make sure you use attraction. And this is a comparative word, it is weaker. Okay, so explain in terms of structure and bonding why the melting point of sodium fluoride is high. Now this really is a GCSE question. And in GCSE, this might have been a 4-mark question, and I think it isn't necessarily totally clear what exactly they want you to say to get those 2 marks. There are a variety of things that you could refer to. So, I mean, the fail-safe option is to write as much as you can, but make sure it's correct. So, again, we've been talking about electrostatic forces of attraction. Please don't just say strong forces. You must say of attraction, right? It's not enough just to say forces or strong forces. And why has that attraction come about? Well, it's come about because there are oppositely charged ions. And then a consequence of that, which is what the 2nd mark is, well, that means then if you have these strong forces of attraction, and we've explained what they're between, then that's going to require a lot of energy to overcome. Now, I appreciate there is a certain amount of, well, I thought they might have meant giant lattice, or all sorts of variety of things that they could have referred to. But still, if you'd included giant lattice structure, then fine, that would have been okay. It wouldn't have cost you any marks. So this was a question I think that a lot of people struggled to answer. So we've got this unusual ion, something that we've not perhaps ever seen anything like before, so an H2F plus ion, and they tell us it's formed when hydrogen fluoride gains a proton, and it shows us that in the equation, and then it asks us to name the type of bond formed when HF reacts with H+, and then explain how this is formed. So I think something that helps us to look at that is the dot and cross diagram. So if we draw a dot and cross diagram for the species on the left-hand side of the equation, we can see our hydrogen fluoride gas there, so it's a covalently bonded simple molecule. We've got our H+ ion, which has no electrons around it. I mean, that's how it's become positively charged. And if you think about how you could stick those together, because that's really what's happening, we're saying that it does say the type of bond formed when HF reacts with hydrogen, so we've got to sort of stick them together. And then we're actually looking at something like this, and so what you can see is that H is just stuck on to that pair of electrons there on that fluorine atom. And we can see that they've come from the fluorine because we've kept that cross, the fact that they are 2 crosses. So the type of bond that we describe as excuse me, when both electrons have come from one atom, is a dative or coordinate bond. And then our explanation is like basically how are we explaining that we've determined it to be a dative or a coordinate bond, is to say that, well, actually both the electrons in that bond have come from a single atom, and in this case have come from the fluorine atom. I did see some answers where people said fluoride ion or whatever, but that's why if you focus on your dot and cross diagram, you can see there is no fluoride ion, right? This is a simple molecule with covalent bonding. So the next question is asking us, or giving us again two unusual ions. It's asking us to draw the shape of the two of them and then include any lone pairs that influence the shape. So that's very, very important. So whenever you draw a molecule and you draw the shape of it, if there are any lone pairs present, they must be shown because they are going to influence the shape. And then we have to name the shape. So thinking about how we can approach it, I haven't really sort of spelled this out too much, but SB or antinomy. And so the way to approach this is how many electrons or what's the group number that we think of for that particular element. So antinomy is in group 5, so 5 electrons. And then we basically then add, well, how many atoms are attached to our antinomy? So 6. And then we either, well, if it's neutral, we leave it like that. If it's got a 1- charge, we add an electron. And if it's got a plus charge, we take away an electron. And so we're adding all of the electrons. These are going to be all of the electrons that are going to be surrounding the antinomy. So 5 because it's in group 5, 6 because it's forming covalent bonds with 6 atoms. So they're each going to sort of bring an electron. And then we're adding another electron because we've got a 1- charge. And then we divide it by 2, and that's going to give us the numbers of pairs of electrons. And then we would look at our total number of pairs of electrons and compare it to our number of atoms that are joined to antinomy, and they're the same. So that means all of those pairs of electrons are bonding pairs. If we look at, so I'm just getting things ready to draw the shapes. If we look at the H2F plus ion, so our central atom has to be the fluorine. Fluorine is in group 7. So it's 7 electrons. It has 2 atoms joined to it, 2 hydrogen atoms. So we add 2. However, we've got a 1+ charge, so we subtract an electron. So that adds up to 8. We divide it by 2 to get how many pairs of electrons there are. So there are 4 pairs in total. We have 2 atoms joined to the fluorine, so that means we have 2 bonding pairs. And that means then that the other 2 pairs not accounted for must be lone pairs. So when we draw these shapes now, the SBF6- has to have 6 pairs of electrons, and all of them are going to be bonding pairs. And the H2F plus has got to have 4 pairs of electrons, 2 of which are bonding pairs and 2 of which are lone pairs. So there is an onus on you to remember what shapes those would actually produce. So we get an octahedral shape with the SBF6- ion, and they didn't penalise you for forgetting the charge, and they didn't penalise you for not putting the square brackets, but for the point of accuracy, that's really what we should be doing, and it is an octahedral shape. With the H2F plus, we said 2 bonding pairs, 2 lone pairs, and if you think about molecules that you might think or might remember have but the same as that, water has 2 bonding pairs, 2 lone pairs. So it's going to, that's how we would draw the shape. So we've got to make sure we show the lone pairs. They've got to make sure they're present. Again, really, we should be having our square brackets and positive charge, and that will have a bent shape, or we describe that as having a bent shape. Okay. So here we've got a bond enthalpy calculation, and so I've just used the colours here just to make it clear where the bonds, how many of each bond there are. So on the left hand side we've got 2 of the carbon-hydrogen bonds and 1 carbon-carbon triple bond, for example. And it's just really to sort of get things ready. It really helps a lot actually to have displayed formulae drawn out, I think, although you've just got to remember that you've got 2 in front of you. So maybe one approach to have taken maybe is to cross out the 2 and to draw another HF just to sort of really spell it out. We just sort of we just write out what we know for sure. Okay, so we know that bonds broken minus bonds made equals the change in enthalpy, and they've given us the change in enthalpy. It's up here in the top right hand corner. So they've told us that minus 179 equals the bonds broken minus the bonds made, and the bonds broken are going to be the left hand side bonds, and the bonds made are going to be the right hand side bonds. And we're trying to work out CF. So there's the bonds broken. So just keep it all together in one sort of like calculation. There are the bonds made, but don't forget we've got plus 2y because we don't. That's what we're trying to determine the value of those there. Put the numbers in. So again, you know, students ask about exam technique, and I'm going to mention it probably quite a lot during this video. But really setting your work out clearly, it's not just for the person marking your work, but it really does minimize the chance that you're going to make a mistake, or reduces the chance you're going to make a mistake. So write the calculation out, write the answers to those calculations, and then start to sort of sort things out. So, you know, we can now resolve this. We get 2y equals 968, and therefore y equals 484. Okay, I mean, wasn't too bad. You just had to be careful, I guess, because it was a bit unusual to be asking you for a particular bond. So where people could make mistakes is they could have these are the wrong way round. They could be bonds made minus bonds broken, which is wrong, of course, or they may have miscounted some of the bonds. We come to time of flight spectrometry, and they give us 3 compounds and their molecular formulas, and you might not have time to do this in the exam, but you know, for the purpose of this, I just did their MRs. And then this was the first time they ever asked a question about ionization using electrospray ionization. So every other question they'd ever asked where we'd had to explain or describe how molecules were ionized had always been about the sort of firing high energy electrons at the molecule. But this one was about electrospray. So it was hard in the sense that students won't have had much practice of sort of writing this out and explaining it. And it's 3 marks, of course. So the first mark, you had to make it clear that it was dissolved in a solvent. That solvent will be volatile because we need it to evaporate easily, but really it was dissolved in a solvent. You didn't need to know it was methanol. They weren't absolutely specifying you had to say that it was injected into a hypodermic needle, but really what they were wanting to make clear that it was basically going to have a high voltage or a positive charge or positive terminal. It was going to be applied to it, right? So a high voltage was going to be applied to it, and the consequence of that high voltage was that the solvent ionized, and then the key bit. So it's the bits in color that are really the marks. The molecule then, you could just say it had a proton. It gained a proton, but an H+ ion is a proton. And actually, I think it's better in the long run if you think of this as an H+ ion and not a proton. Particularly when we look at the next question, that will make your life a little bit easier. So whatever X was now becomes HX+. So we've added that H+ ion. So we've got to remember we've added a hydrogen, but also it's now a charged species. It's now an ion. So very, very few people got this next question right. And curiously, I mean, it's not the easiest, but one of the things that was curious about it all was that actually very few people actually even wrote an ion. So they had just explained that something gained a charge, and then they were asked to then say, okay, so what then gets detected at the end? And they even say ion, and people were not writing a formula that was a formula of an ion. Now, I think if you've written proton as part of your explanation here, I think it does make this a little bit harder, because if we think of it instead as a H+, then we're going to be more aware that we have to accommodate that hydrogen in our formula. So we have to go back to the beginning, and we have to think these are the 3 possible molecules that could be detected. And It's asking us which one reaches the detector first. Well, it's going to be the lightest one, or the one with the least mass, or the smallest mass. So that's the first one at the top here, C3H5O2N. But we have said that as part of its ionization, it has gained a proton. So we need to add that, as it were, to the formula. So when we actually look at our formula, when we actually look at our formula, we have the formula that we're given here, but we've added a hydrogen, so it's C3H6O2N. And then, strictly speaking, if it's an ion, we should be having our square brackets, and then we should definitely be having the positive charge. Okay. Something else just to say while we're on this is, when you look at information at the beginning of questions, if you get any information like we have here, that is before the first actual question or the first thing that you actually have to answer, then what you've got to remember is this information could be relevant for any subsequent question part. So this could be relevant for 2.1, 2.2, 2.3, etc. Okay, so just bear that in mind. Sometimes in the final A-level papers, you can be given information at the beginning, and the rest of the question might go over, I don't know, 5-6 pages, and the final question, as out of those 5-6 pages, may rely on information that was there at the very beginning. So just please be mindful of that. This was relatively straightforward. You had to do a first ionization equation for germanium. So you had to make sure you used the right symbol for germanium, and they did spell out, including state symbols, and there is always the odd person who forgets to do that. That's where the proton has been added. I have to remember what things I've written on here. And so there's our first ionization equation. So we had to make sure it was gaseous, and then of course you could have had germanium plus an electron goes to germanium plus 2 electrons, because you could have been thinking about the electron that was being fired at it, but it doesn't really matter. Okay, so this is a 5-mark time of flight question. So these can be, by the time you get to the final exam at the end of year 13, these really should be. Everyone can make mistakes, but this is where you should be hoping to get 5 marks, because it's not an unexpected question. It's not something that you can't be prepared for. There's been a mathematical time of flight question in, I think, every single AS and A-level paper, set of papers, right? So in every AS and A-level exam. There are common areas where people fall foul. One thing is to be really mindful of the units. So this kinetic energy equation here is, if you like, I know it sounds a bit ridiculous, but it's a physics equation, which means that when we think of the units, we have to think in terms of physics. So we've got to think about meters when it comes to distance or speed, or velocity, sorry, and then we've got to think of kilograms in terms of mass. So physics is a subject that deals with kilograms, whereas chemistry deals in grams. Something else to add, and this is true for any question, is that if they give you a value, and they've given us 4 here, they've given us 4 numbers, we will have to use every single one. So they never give you a superfluous number or superfluous value ever. So when you get to the end of a question, particularly if you haven't felt very confident about it, or even maybe if you're stuck part way through, one of the things to just ask yourself is, have you used every single number that they have given you? Because if you find you haven't, particularly if you feel you finished the question, you will definitely have made a mistake. Okay, so let's work through this then. Now, a lot of people just went straight to a sort of rearranged kinetic energy equation in which they had substituted V equals d over t, velocity equals distance over time, and they were straight away they were wrong, because they had rearranged the equation clearly in their head, or I don't know where, but they hadn't done it on paper, and it was wrong. And the moment it was wrong, that sort of basically stuffed up the rest of the question. Yeah, there are transfer of error marks, but it's very difficult to give transfer of error marks when the equation being used is just wrong. So always try, you've got to try and make life as simple as you possibly can, and please, when I say write everything out, it's there to reduce the chance of you making a mistake. So were there any of these values that we could use quite quickly? Yes. So we know we're going to need to use half mv squared because we're being asked to calculate mass. But we know that we've been given a distance, and we know that we've been given a time, and we know there's a relationship where velocity equals distance over time. But rather than just substitute d over t into our equation, just work out what v is. It will make your life so much easier. So we have to remember that the distance they gave us was in centimeters, so we needed to convert it to meters, and then we do the time and we get our velocity. Fine. Next then, we've got our kinetic energy equation, and then the way we proceed from there is, well, let's rearrange it so that mass is the subject. So we want mass to be the subject, so we rearrange our equation so it's 2 times the kinetic energy over v squared. So if we're trying to work out a particular term, make the term the subject of the equation before you put any numbers in. Something else that I find students do is they would have put numbers in straight away from the beginning here, and then they would have tried to rearrange with the numbers. No, just rearrange with the terms, get the thing that you're trying to find as the subject, and then stick the numbers in. So it's very straightforward. We've got our velocity, so our denominator is going to be velocity squared. It's just 2 and then times the kinetic energy which they gave us. So by the end of this calculation, we have used the first 3 values that they've given us. And we have got now a value for the mass, which we've got to remember is in kilograms. So get into the habit of writing units as you're working through in kilograms for an ion, right? You've got to remember that what you're measuring here is a single ion. So that's why we have an incredibly small mass. So we have worked out now the mass of one of these germanium ions. So the next thing we need to do, and the first part of the final answer, is we have to work out the mass of 1 mole of germanium ions. So 1 ion equals this. We've got to work out what 1 mole of those ions are. And now we know, and this is why they've given us the 4th value, we know how many particles there are in a mole. So we have to multiply the mass that we have here of 1 germanium ion by the number of ions that would be present in 1 mole of germanium ions. So we multiply them by Avogadro's constant. And we get a value which, again, we've got to remember is in kilograms. Okay, so we've got to remember that answer is kilograms. So we need to convert it to grams because the unit they've got in the final answer at the bottom there is in grams. So we have our mass of 1 mole of germanium ions. And then it asks us for the mass number of the ion. Now, we're talking here about a particular isotope. We are not talking about the relative atomic mass. We're talking about the mass number of a particular isotope. So in those instances, your number has to be a whole number, has to be an integer. So this is where we remove any decimal places. It must be a whole number, and our mass number of our ion is 69. So now they're moving on to chromium, and they ask us to complete the full electron configuration of chromium. And it's interesting, when you did the electron configurations of the transition metals, or in fact electron configurations in general, you had a system. And then when you did the transition metals, you came across 2 anomalies to that system. And they're the anomalies, but they're often the common questions. And the 2 anomalies are chromium and copper. And notice that chromium is the one we're asked about. And the anomaly is that when you fill up the subshells, you actually only have 1 in the 4s subshell. And so we have 4s1, 3d5 as our final part there. Anything else? So if it had been vanadium to the side, it would have been 4s2 3d3, and if it had been manganese to the right, it would have been 4s2 3d5. But chromium and copper are the anomalies where they would have a 4s1 sublevel. And then this one, so few people fell a bit foul here, started putting things like relative atomic masses and actually also got the wrong element. It says an atom, right? So you've really got to pay attention to the fact it says an atom. So we're talking about a single particle, and we're told it has 2 more protons and 3 more neutrons than chromium-52. So there's chromium-52. They didn't tell us what the atomic number is, but if it's chromium, it has to be 26. And they told us it had 2 more protons. So that means our atomic number is going to change from 26 to 28. And then when we look at, chromium is 24. Oh, I see, I've made a bit of a mistake here. Sorry about that. Right, let me just fix that. That doesn't help, does it? That should have been 24. Sorry about that. Okay, so right, so chromium has an atomic number of 24, and we are adding 2 more protons, so we're going to an atomic number of 26, and that is iron. So our element is going to be iron. And then when we look at our mass number, protons and neutrons both have a relative atomic mass of 1. So we are adding +2 and +3 to 52. So we're taking that to 57. So when we look at our answer is iron 57, right? And there's no relative atomic mass because we are talking about an atom. Okay, the next question was to work out. Well, it was actually mass spectrometry again, but they wanted us to determine the percentage abundance of the 4th isotope. Well, really, there couldn't have been anything simpler. They've told us that these are 3 of the 4 isotopes. They've told us the abundance of these 3 isotopes. We're told that the abundance is a percentage, so that means the percentage abundance for all 4 of them has to add up to 100%. So all we need to do to work out what the percentage abundance is 100% minus the abundance of these 3 isotopes. And then this is a bit of a strange one. It says show by calculation that the mass number of the final isotope is 50. So there were a variety of ways of doing that. I'm just going to, maybe this isn't the simplest, but I'm going to let the 4th isotope be Y. So if we were doing our calculation, we've got our percentage abundance times mass number, percentage abundance times mass number, etc., etc. And we know that our unknown is 3.6%, and we've let it equal Y. All over 100 because we're doing an average, and these were percentages, but we know that what the average equals. And so when we resolve that, we end up with a value of Y of 49.97, but the point is we know because it's an isotope, it has to have a round number, whole number. It's like the previous question. So a lot of you spotted it here, but not on the earlier question. We end up with the answer of 50, and that confirms that the mass number is 50. Deduce the oxidation state of chromium in Cr2O7 2-. So I'm not sure how well you can read this at the top. It's quite difficult to show, but what we're saying is that we've got 2 chromiums and the oxidation number is Y, so 2Y plus, and then oxygen always has an oxidation number of -2, except unless it's bonded with something more electronegative, which is only fluorine, or if it's hydrogen peroxide, H2O2. And then we've got 7 of them, so 7 times -2, and we know that the answer to that sum of 2Y minus 14 is -2 because that's the overall charge of the ion. So 2Y minus 14 equals -2, therefore Y equals 12. 2Y equals 12, therefore Y equals 6. Then it asked us to deduce a half equation to show the oxidation of iodide ions to iodine, and so really, honestly, there is no excuse now to not remember that iodine has the formula I2. So you're going from I minus to I2, so we have to balance that both in terms of number of iodine atoms and also in terms of charge. So there we go. And then it asked us to deduce the half equation for the conversion in acidic solution of dichromate ion to chromium 3+ ions. If you're asked to do a half equation and they mention either acidic solution or they say water, don't worry about it, because when you do your half equation, those things will appear, right? They'll be taken care of if you follow your normal, if you follow the steps that you should follow when you're doing a half equation. So these are the steps to follow. So first of all, write your formulae of what you're starting with and what you're finishing with. So we would be starting with our dichromate here, and we would be finishing with Cr3+. Balance any element that's not hydrogen or oxygen, so obviously the chromium. So we'd be starting with, there would be 2 chromiums in our dichromate, but only 1 in our Cr3+. So we would be putting a 2 in front of that Cr3+. And then we would look at the oxygens on each side and add waters to balance the oxygens. Then we would look at the hydrogens on both sides and add H+ ions to balance the hydrogens. And then lastly, we would add electrons to balance the charge. So our overall equation here, and I've tried to do the colours to sort of reflect the steps, is given. And if you notice that we have 14 H+ ions as part of our equation, so we have taken care of the fact that it's an acidic solution. Just as a sort of slight aside, in the oxidation of alcohols, when you use potassium dichromate, you have to remember, don't you, that you have to say it's acidified potassium dichromate, and if you don't put the acidified, then you don't get the mark. And that's because this is the relevant half equation for the oxidation of, well, this is one of the half equations for the oxidation of alcohols. And without those H+ ions, the reduction of the chromium wouldn't take place, and therefore the oxidation of the alcohol wouldn't take place, and that's why it needs to be acidified. And then it says, use your answers from questions 3.5 and 3.6 to deduce the overall redox equation. So we are simply adding together these two half equations, but we've got to do it so that the electrons, and you'll notice it's on the left for one and on the right for the other, those electrons have to cancel out. So those are the two equations written out. We can see that there's 6 on the left and 2 on the right, so they are not going to cancel out. So what we will end up doing is we multiply the top half equation by 3. So it's going to be 6i minus goes to 3i2 plus 6e minus. And then when we add those two half equations together, the electrons cancel out. You would also cancel out any H+ ions and any water molecules if you could, to simplify it as much as you can, and then this is our overall redox equation. So 6-mark question. So first, ionization energies of the elements in period 2. So one of the things that was quite interesting with some of your answers was that I think when you did this, when you would have done this in school or in class, you would have applied it to period 3. But what they're doing here, that's mixing it up, if that's the right way of phrasing it, is they're looking at period 2. But a lot of you wrote answers talking about period 3. So please watch out for that. It meant you were sort of either in autopilot or doing something else, but you weren't really thinking about what you were writing about here. So obviously you don't have to draw what I've drawn here, but this is what we're trying to describe. So this is what you have to have sort of remembered or visualized in your head to really answer this question appropriately. So we've got period 2 going from lithium to neon. And if we were plotting the ionization energies, that's what the y-axis is. The first ionization energies, then the shape would look something like this. So the first thing to comment on is that there is a general trend, right? So the first 2 marks, or 2 of the marks, are going to refer to the general trend. And we've got to explain why that is, because notice there's a word explain. So explain means say what it is and then why it happens. And then we can also see that even though we've stated that there's a general trend, there are 2 anomalies to that general trend. So when we go from beryllium to boron, it's not following the general trend, and when we go from nitrogen to oxygen, it's not following the general trend. So we're going to we're breaking our answer down into 3 parts. Each of them are basically worth 2 marks. The general trend, the first anomaly, the second anomaly. And I think, it helps you when you're writing long answers to sort of 6-mark questions. I don't know, you don't have to use little subheads or anything, but just give yourself, think of it as contained pieces of information. So the first thing we would say is that the first ionization in general increases as the atomic number increases, or as you go along the period. And the reason for that is we have an increasing nuclear charge, or we've got an increasing number of protons. They weren't actually that bothered in the Mark scheme about decreasing atomic radius, because actually that is a consequence of the increasing nuclear charge. But still, it is true. So we're focusing more on the increasing nuclear charge, and then we're explaining then why then that means there's a higher first ionization energy. So a higher nuclear charge means that we have a stronger attraction or between the nucleus and the outer electrons, and so it requires more energy to remove an electron to form that 1+ ion. So that sort of paragraph there, which is slightly more than we needed, would have been 2 of the marks. And then we would have said there were 2 exceptions to this trend, and then we would have gone into the first exception. So this is another 2 marks. So you have to be very clear that when you're stating something as lower, you've got to state what it's lower than. It's not enough to say boron is lower. You've got to say it's lower than beryllium, and that is against the trend, you see. So if you're using words that are comparative words like lower, stronger, further, whatever, you've got to say than what. So boron has a lower first ionization energy than beryllium, and then we have to explain why. And again, if you're making a comparison, so it's not enough just to say beryllium has its boron. Oh, I've got that a little mixed up there, haven't I? So boron has its outer electron in the 2p sublevel. It's not enough just to state that. You've got to say, whereas in beryllium, it is in the 2s sublevel. Sorry, I'm just going to correct that because that is also quite annoying, isn't it? So it's boron, okay, that has its outer electron in the 2p sublevel, and it is beryllium. So sorry about that. That has it in the 2s sublevel. So that's a statement. That will be one of the marks. And then the next mark would be that why that makes a difference. So the 2p sublevel is higher in energy, and therefore on average that electron is further from the nucleus, and therefore it's easier to remove. Okay. And then finally, we see from our graph that oxygen is lower than nitrogen, or the first ionization energy of oxygen is lower than that of nitrogen's. So that's a statement recognizing that is important. And then because its outer electrons in the 2p orbital begin to pair, or there is the first pairing of electrons in a 2p orbital. And by saying it's the first pairing, I think it is clear that nitrogen doesn't have that pairing. So that results in a slight repulsion, which makes that first electron easier to remove. And so essentially it was 2 marks for each. There were essentially 3 paragraphs in my answer there, and each paragraph made up 2 of the marks. Okay, so here's an equilibria question. So I've, just recognizing the fact that we've been given 3 numbers, so we're going to have to use all 3 of those numbers. And then the way to approach this is, I think it does make it easier in this example to rewrite the equation. And I always, whenever I write a reaction equation, I always write the ratios above. I know you might think, well, why? Because they're written before the formulae, but I just think it does really spell things out to me. And then because this was equilibria and we're looking about a change from the beginning to the end, please just remember this ICE acronym. So initial, change, equilibrium. Okay, so we're going to write the values. So we were told these values of 1.5 and 1.00, they are the values. It says they are mixed together, but that means we've got two containers. One contains 1.50 moles of NO and one contains 1.00 moles of Cl2. And before they're mixed, that means we clearly don't have any of the product, right? We don't have any of the product. So that's clearly 0. And then they tell us that when it reaches equilibrium, we then have 0.350 moles of the NaCl. So all I've written so far is the information that they've given us, but I've written it by recognizing that there's an initial, there's a change, and there's an equilibrium. So it helps to draw this little sort of table out, really. So now I know what the NaCl was at the beginning, I know what it was at the end, so therefore I know what its change is. And then when I look at the other, the NO and the Cl2, their changes are going to be related to the change of the product, but we've got to remember about molar ratios. And if the product increases in an equilibrium, then the reactants must decrease. So these are all going to be minus something. And then what they're minus of will be a molar ratio of the change in the product. So it's a 2 to 2, so a 1 to 1 ratio between NO and NaCl. So if NaCl has increased by 0.35, then NO must have decreased by 0.35. It's a ratio of 1 to 2 of chlorine to NaCl. So if the NaCl increased by 0.350, then the Cl2 must have decreased by half that amount. And then we just subtract those changed values from the initial values and we get our equilibrium values. And then they asked us to give the expression for the equilibrium constant Kc for this reaction. So you've got to remember, so when they ask for an expression, they don't want any numbers in there, right? They want the terms, and the terms refer back to the original equation. So remember, it's products over reactants. Remember that they multiply each other, and remember that the stoichiometric value or the molar ratio value or whatever, that is, the square brackets are, that is to the power. So the concentration is the power of that stoichiometric value. So our product was NaCl, so that's on the top, it's the numerator, and it had a 2 in front of it, so that means the concentration is squared. Cl2 and NO were reactants, so they're on the denominator. They multiply each other, they don't add, they multiply each other, and then we only had 1 chlorine, so it's the power of 1, so we don't need to write that. And we had 2 NOs, so it's the power of 2. So we've just got our expression. Okay, so a lot of people struggled with this question, and it does actually build on what you've been doing, or certainly on the previous question. It certainly builds on that. So it's asking us to determine the amount in moles. Okay, so we're going to pay attention to that, the amount in moles of NaCl. They're giving us the moles of NO and Cl2, but they've also given us a volume. A lot of you fail to use this volume at all, and to remind you of what I said earlier, if you're given a value, you will have to use it, right? So if you haven't used it, you've made a mistake. So that should be, again, it's sort of like, it's feedback. It's telling you that even if you felt confident in what you're doing, if you fail to use one of the values, then you've made a mistake somewhere, and you've got to think about, well, where was it I should or was supposed to use that? So I'm going to start with the expression that we wrote to the previous answer, and they're asking us to determine NaCl. And they have given us information about NO, they have given us information about Cl2, and they have given us information about Kc. Now, exam technique, right? So many of you just stuck numbers into this expression, and yet your unknown was here, and then you had numbers here, and numbers here, and number here. Oh, it just, honestly, it just makes it so much more likely that you're going to make a mistake. Rearrange the equation so that the thing that you're trying to find is on its own, that it's the subject of the equation. So multiply both sides by Cl2 and NO squared, right? And then square root it. You don't have to do that at that point, but square root it, because it means that once we've determined what numbers go in here, we literally just switch our calculator on, write the square root sign, write the numbers out, and press equals. There's no faffing around with numbers. It's just, there's the calculation, ready to go, boom. Now, you've got to pay attention to what these square brackets mean. They mean concentration. And they haven't actually given us the concentration. They've given us the number of moles. That's why we need this volume here. So, okay, so that's, sorry, make sure you're, I was just reminding myself there, or reminding you really. The concentration of NO is going to be the number of moles. Remember, concentration is moles divided by volume. Remember that volume has to be in decimeters cubed when you're doing concentration. So we have to actually work out what our value for the concentration of NO is, and we have to do it also for chlorine. So this was a thing that a lot of you forgot. A lot of you just dived in, wrote this expression, and just wrote numbers in here, and the numbers you wrote were just the mole numbers, not concentration. So you hadn't really taken time and care to sort of establish the situation before you started to do the final calculation. So that was a big classic mistake. And now we're all good to go, right? We're all ready now to fill in the numbers. So we've got everything. There's our Kc that they gave us in the text, and these are the concentrations that we've worked out. And we just plug them into our expression, plug them into our calculator, and we get an answer. But what we've got to realize is that what we've actually worked out here is the concentration of NaCl. And they actually want us to work out the moles. So, you know, if you inadvertently stopped here, you still would have got, I think, 3 marks. So, it's, you know, you've been doing it correctly, you just haven't got all the way to the end. So how do we do that? Well, we use our volume again, and we know that moles is volume times concentration. And so there's our number of moles at the end, and there's our value. But actually, this has been a very good question, I think, in terms of trying to explain to you or trying to point out exam technique. And I can't emphasize enough getting your equation ready so that the thing you're unknown is on its own before plugging numbers in. All right, so titration. Again, like, you know, I know I'm going to have to use this reaction equation, but it's really only going to be about the reactants. So I do put my molar ratios. They're going to be important. I'm just highlighting my numbers because I know these are also going to be important. The fact they've given us milligrams, that should be like a warning, or, you know, a recognition. Oh, okay, I'm going to have to probably take that into account and think of it in grams at some point. They've given us a volume and a concentration, so that's really great, because straight away you can work out moles, and then they've given us a table of results, and you'll see why these are highlighted in a second. So they're asking us to work out the MR of H2A. So there's H2A, and they're asking us to work out the MR. Now, if we're going to work out the MR, we're going to have to work out concentration, etc. Okay. So first thing first, though, is straight away they've given us a volume and they've given us a concentration of aqueous sodium hydroxide, so we should work out the moles. So we have straight away worked out that we have used 2.8 times 10 to the minus 3 moles of sodium hydroxide, and we have a molar ratio. So we know, therefore, that how many moles of the acid we've used, or that must have been present, sorry. So it was half as many moles as the sodium hydroxide. And we know those moles of sodium hydroxide were in the burette, so they refer to the volume that we added to our 25 centimeters cubed of sodium hydroxide. Now, we need to work out what our mean titra is. And mean titras, they never use rough, okay? So rough values are never appear or never used as part of a mean titra calculation. And then beyond that, we choose results that are concordant. And results are concordant if they are 0.1 centimeters cubed within each other. So that is why I have highlighted those two values in orange because they are concordant results. They are within 0.1 centimeters cubed of each other. So our mean titer is those two values, is the average of those two values, so 26.45. So that means we had 1.4 times 10 to the minus 3 moles in 26.45 centimeters cubed. So that's what we've stated. Now, that 26.45 centimeters cubed came from our original. So we originally dissolved all of our acid in 250 centimeters cubed, and then 26.45 of that 250 centimeters cubed has had 1.4 times 10 to the minus 3 moles in it. So we need to work out how many moles was there in our 250 centimeters cubed. So it's going to be the 250 divided by the mean titer. So it's a scale up, right? We're scaling it up. So we must have had in our very original sample 0.0132 moles. We know that the mass of 1300 milligrams must be that number of moles. So we know that MR is mass divided by moles. We've got to remember to turn the mass into grams. So we end up with 98.24. And actually, it probably should be 98.2. Really my final answer, because we've got some of the values of 3 significant figures, and we always do our correct number of significant figures is what corresponds with the values with the fewest in our information. Okay. Then they've got an uncertainty question. So the uncertainty in using the pipette in this experiment is plus or minus 0.06 centimeters cubed. Calculate the percentage uncertainty. So percentage uncertainty is the uncertainty value times the number of readings. So we would only have taken one reading with a pipette, divided by the measurement, or divided by the range, or divided by the amount that you've actually measured. So the only thing where people made a mistake here is they mostly did it correctly, but they didn't pay attention to the fact it said pipette and that the pipette was a 25 centimeter cubed volume. So there's our uncertainty. It's one reading. It's divided by the volume that the pipette measures, and we end up with 0.24%. Now this question, I think a lot of you understood why it was a problem, but the reason that a lot of you failed to get the mark was that you didn't really express it in a clear enough way. And the mark scheme is a little bit funny about this, but the version from the mark scheme I've decided to go with, I think, is a good answer and is a lot clearer than what a lot of you gave. A lot of you said, "Oh, when the air bubble, when you open the tap, the air bubble comes out before the liquid and all that sort of thing." I think the point is the volume you're measuring. Some of that volume is the air bubble. So just make it clear that the air bubble is taking up volume that you would normally, that would have otherwise been filled by the solution, and that's really, I think, a good answer. And then during the titration, the student washed the inside of the conical flask with some distilled water. And why is that not a problem? Because what are we measuring in the titration? We're measuring the number of moles, and adding water does not affect number of moles. It does affect volume, and it does affect concentration, but it does not affect the number of moles, and that is what we're actually measuring. Okay, so this one. Now look, they've told you it's titanium 4 chloride, so there is no excuse for getting the formula of titanium chloride wrong. So that Roman numeral 4 is essentially telling you the charge on the titanium, so it's telling you it's titanium 4 plus. So you're going to need 4 chloride ions. Now magnesium is a group 2 metal, so when you make magnesium chloride, it's going to be MgCl2. So your equation, you do have the information to be able to produce this equation, and you just then needed to balance it. So it was titanium chloride plus magnesium goes to titanium plus magnesium chloride, because they are talking about the extraction, so you know you're going to end up with a metal titanium at the end. Now the role of magnesium. Now a number of you talked about it, that the magnesium displaced the titanium. At key stage 3, you did displacement reactions. At key stage 4 in your GCSE, when you did chemical changes, you did redox, and you did what you had always thought of as displacement reactions. But you were talking about them, you were already starting to talk about them at GCSE as redox reactions. In fact, I think I'm right in saying that GCSE mark schemes tend not to even accept displacement, right? So this is not a radical change. Displacement is not a real thing, really. Like, it was fine at at key stage 3, it's fine, but displacement isn't a real thing. What you've got is reduction and oxidation happening. So you have to think, well, what is the role of magnesium? So what is happening to the titanium? The titanium is going from +4 to 0. So it's being reduced. So the role of magnesium is as a reducing agent. The reason displacement doesn't really work is if you think about a lot of the reactions that you did, like adding zinc to copper sulfate, and then you got as a product copper and zinc sulfate, and it looked like they were swapping partners. At GCSE, you realised, or you learnt, that copper sulfate wasn't copper and sulfate stuck together. They weren't paired up. In solution, they are completely separate ions. So the sulfate ions were just hanging around doing nothing. They are spectator ions. What was happening was that the zinc was going from zinc to zinc 2+, and the copper was going from copper 2+ to copper, but they weren't swapping partners. There was no displacement really going on. Okay, this question 7.2, a lot of you I think found this a bit tricky, and I think it's tricky with respect to appreciating what it is you've got to do, and that often is what makes chemistry calculation questions hard. The actual calculations are not really that difficult. You're never doing more than multiplying or dividing or whatever, but what you do have to recognise though is how you go about determining the final answer. And they've told you that you've got a mixture of magnesium oxide and magnesium hydroxide, and they told you what that mass is, and you're going to have to work out what the percentage of one of them is in that mixture. And then they give you 2 reaction equations, and they give you a mass of water that's produced. So really, this has got to be our starting point, this mass of water that's produced. If we know if we know the mass, and we certainly know the formula of water, then we can work out the number of moles of water. And look, there's a 1-to-1 ratio. So however many moles of water were produced, there must have been that many moles of magnesium hydroxide. And then once you have the moles of magnesium hydroxide, you can work out the mass of magnesium hydroxide. And once you have the mass of magnesium hydroxide, you can work out you can work out how much magnesium oxide was in the original mixture. So turn our milligrams into grams, because we've got to remember that. Then we work out our moles of water. Therefore, and that's what the reaction equation is there to say, is that, well, if we know that's how much water was made, we know how much magnesium hydroxide we had in the first place. If we know how much magnesium hydroxide we had in moles, then we also can work out what mass there was in the first place. So, it's relying on using your periodic table and so on. Therefore, the mass of magnesium oxide must be the mixture's mass minus the magnesium hydroxide's mass. So we get 2.52, and then we're just doing a simple percentage. Okay. Okay, so appreciate that because of lockdown you haven't really had, or you didn't have the opportunity to do some of these tests. You had done some of them, of course, but you hadn't done all of them, and you hadn't done an exercise where you would have done a variety of different substances and tried to work out what they were. But anyway, if we're going to add a reagent that's going to distinguish between two unknowns, so we look at the first one, and we can see that the chloride is the same. So we're not going to be able to distinguish anything to do with the fact that they've got chloride, but we are going to have to distinguish the fact that one of them's sodium and one of them's barium. Now, so that means that this is about group 2, right? Because so when you think about your A-level topics, you did in the inorganic section, you did group 2 and group 7. So that means group 2 is going to matter here. And you need to remember the fact that there was a barium compound that was very insoluble, and that was barium sulfate. So you needed to add any sulfate, basically, any soluble sulfate, I should say, sorry. Sulfuric acid, sodium sulfate. And then with the sodium chloride, there would be no change or no observation. And then with the barium chloride, there would be a white precipitate formed, and that would be our way of distinguishing between those two compounds. On the next one, we can see that sodium is the same. So we've got a chloride and a carbonate. So there are actually a couple of options we've got here, but I'm going to focus on the simplest. And the thing is, I think you've got to recognise that carbonates, sodium carbonates, are bases. And the fact is that when they react, if there's a neutralization reaction with a carbonate, you get carbon dioxide produced. And if that's taking place in a solution, then you're going to see bubbles or effervescence. So it really is the simplest thing is to add an acid, and then you would get no observation or no change with sodium chloride, and you would get effervescence or bubbles with sodium carbonate. You could have done acidified silver nitrate, so you would have got a white precipitate with the sodium chloride, but you would have actually also had to have realised that because the silver nitrate was acidified, you would have also got bubbles, so you would have actually seen two things. So that's why I chose not to do that one, but you could have done that, and some people did, but got one of the observations wrong. Okay, so we're going to look at just going to finish now by looking at the multiple choice questions. All right, so in some cases you have to do a lot of working out, and in other cases it's just a process of quick elimination. So they're asking us for the greatest number of particles. So really we have to work out how many moles are there of each of these. Basically all of these are going to be, I guess, times by Avogadro's. So it's the number of moles times Avogadro's is going to give us the number of particles. So it's a half for hydrogen, and it's a quarter for helium. And you've got to remember that the molar volume of gases is 24 decimeters cubed, so it's 1/24 for the volume of hydrogen molecule when we think of 1 decimeter cubed of hydrogen, and the same for helium, sorry. So clearly the biggest number is going to be, half is bigger than a quarter and bigger than 1/24, so it's got to be the 1 gram of hydrogen molecules. What is the molecule of, what's the empirical formula of this oxide? So write the elements, but there's 2 elements here, so molybdenum and oxygen, and then write the masses and divide those by the atomic masses. So 4/96 and 1/16. And then you'll have 2 numbers. You divide through by the smallest. If you get like a half or a third or a quarter, you're going to have to multiply them, so you've got whole numbers. So we've got 1 to 1.5, so we're going to multiply them both by 2 to make them sort of integers, to make them whole numbers. So we get 2 to 3, so that means it's MO2O3, so it's C. Straightforward, right? Delocalized electrons only feature in metals and graphite, so that's pretty easy. Okay. Which species is not pyramidal in shape? So trigonal pyramidal, and it could have been a different pyramidal, but actually it was all focused on trigonal pyramidal here. And that's, if you can remember, it's helpful for you to remember that trigonal pyramidal is a consequence of 3 bonding pairs and 1 lone pair. So if we think about dot and cross diagrams for those 4 substances, or we think about how working them out. So phosphorus is in group 5. There are 3 atoms stuck to it. Divide it all by 2. So we've got 4 pairs of electrons, 3 atoms attached. So 3 bonding pairs, 1 lone pair. So that is clearly pyramidal. H3O plus, 6 because oxygen is group 6. 3 because there's 3 hydrogen atoms. Minus 1 because there's a +1 charge. Divided by 2, so that's 4 pairs. 3 atoms attached, 3 bonding pairs, 1 lone pair. CH3 minus, so 4 because carbon's in group 4, 3 because there are 3 hydrogens, and plus 1 because there is a 1 minus charge, divided by 2, 4 pairs, 3 atoms attached, so 3 bonding pairs, 1 lone pair, and then finally BF3, borons in group 3, there are 3 atoms attached, there's no charge, so nothing else to do. 6 divided by 2 is 3, 3 atoms attached, all of them are bonding pairs, no lone pairs, so it's D that is not pyramidal in shape. Which change occurs when water is vaporized? So it can't be an exothermic change, because if you're vaporizing water, you've got to put energy in, so it must be endothermic. Covalent bonds are broken, no way, because yes, we're going from water to steam, but we've still got H2O as our molecular formula, so there's no covalent bonds broken there. Total energy of the molecules decreases if you vaporize them or if you heat it up. Well, that's just bonkers, right? And so what we're overcoming are hydrogen bonds. So yeah, of course, we've got intermolecular forces being overcome. Which equation represents the reaction that has a standard enthalpy change equal to the standard enthalpy of formation? So you've probably got told, or it's probably explained to you, that it was really important that you learn the definitions to things like standard enthalpy of formation. And the reason for that is there is a chance that they could ask you to give the definition, but more likely it's going to be a question like this, where you need to understand the definition to be able to apply it to a particular circumstance. So the definition of an enthalpy change of formation is the formation of 1 mole of a substance from its elements in their standard states. So you have to decide, well, all of them are forming 1 mole, so there's no problem there. So you then have to decide elements. Well, elements straight away rules out B and D because they are ions, not elements. And so then you have to decide between A and C which one of those reflects the standard state. Barium is a metal, chlorine is a halogen, it's a gas, so it has to be C. Which equation does not represent a redox reaction? So sorry, I just have to come out and do these numbers. It's quite hard to do them, reveal them one by one. Really, you could just focus on one, just focus on any metals, or I mean, you just focus on one thing on both sides, because you just need to see that if there is a change in oxidation number, then there must be a redox reaction, because if something's oxidized, something else has got to be reduced. And if we look, D, there's no change. So D, it does not represent a redox reaction. Everything is the same oxidation state on both sides. Which property would you expect the element radium to possess? It is very insoluble, because we know that barium is very insoluble and radium is below barium, and the trend was it got more, sulfate compounds got more insoluble as you went down the group. It does not react with water. Well, again, going down the group, the reactivity with water increased. Good conductor of electricity. What forms a covalent? So it's a metal. So it's not going to form a covalent fluoride because you need there's a rule of thumb. It's a metal and non-metal, but it is a metal. So it is a good conductor of electricity. Same as group 2 again, actually. So we've got strontium and calcium. So one thing that might help us is just to draw strontium and calcium and recognize the fact that they are different size atoms or different size ions when they're ionic and so on. So has a lower first energy than calcium. Strontium would, because the electrons would be further away, and we know the ionization energy decreases down the group, so it would have a lower one, so that is correct. Strontium has a larger ionic radius than calcium. Clearly that's correct. Strontium reacts less vigorously with water than calcium. Well, we know the reactivity increases down the group. In a sense, that there's a correlation between the first ionization energy and the reactivity. So the lower the first ionization energy, the more reactive something is, if you're comparing it in a group anyway. That's a useful sort of it's just a correlation. And strontium hydroxide is more soluble in water than calcium hydroxide. So sorry, I forgot what. So yes, strontium would react more vigorously with water than calcium. can't remember now what I said, so I might have said something wrong, so I'm sorry about that. But obviously they get more reactive down the group, so your strontium is going to be more reactive with water than calcium. And then with the hydroxides, they do get more soluble as you go down the group, and strontium is below calcium. Which property of the group 2 elements increases with the increasing atomic number? So we're going from calcium to barium. So again, it's group 2, we're going down the group. So actually we can refer back to our calcium strontium sort of circles at the top there. Electronegativity decreases down the group. First ionization energy decreases. Melting point decreases. And just to say, this is a sort of useful, again, rule of thumb. The strength of a bond is a sort of is proportional to the force over the radius, so charges over size or distance. But clearly the atomic radius increases as you go down the group. I mean, we could have just said that straight from the beginning, but it doesn't do any harm to look at the others. What is an oxidizing agent? So let's think of all firstly, what's the definition of an oxidizing agent? Well, if something oxidizes something else, then it itself must be reduced. So it itself must gain electrons. Now, if we are talking about something that is gaining electrons, that instantly rules out B and D, because they are already F minus and I minus. They are not going to become F2 minus or I2 minus, right? That's not going to happen. So now we're looking at fluorine and iodine. And iodine, there is a reactivity series, basically, where you can think of group 7 as having a reactivity series where fluorine is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine. So reactivity decreases down group 7, and that is really a reflection of its ability to gain an electron and therefore be an oxidizing agent. A lot of you got this question 20 wrong, which was, well, I think is slightly surprising. So let's think about the equation that's relevant here. Okay, so heat energy absorbed is, whether it's absorbed or released, it doesn't matter. It's energy transfer, right? So it's Q, okay? And then we know that Q equals mc delta T, and m is obviously the mass, C is the specific heat capacity, and delta T is the temperature change. Now, if we substitute our terms here, Q equals M, C, Y. So the answer is A. A lot of you went for B for some reason, but we're talking about a temperature change. Now, I know we quite often measure things in degrees Celsius, but really our unit of temperature is Kelvin. But the point is, a change in degrees Celsius is the same as a change in degrees Kelvin. So if I go from 20 degrees Celsius to 40 degrees Celsius, that's a change of 20 degrees, okay? But it's also a change of 20 Kelvin. It's the same as going from 293 to 313. So it's 20, the change is 20. This question, I guess, is a bit tricky. It's the sort of question you don't get that often, and it's probably one that you need to practice on a fairly regular basis to sort of keep your hand in, as it were. So we're going to consider a before and after. Again, I've written the molar ratios along the top. We're starting with 20 centimeters cubed of butane. We're burning it in the presence of, it says 0.2 decimeters cubed, but let's have that as centimeters cubed. Now, because the molar volume of a gas at room temperature and standard pressure is 24 decimeters cubed, that means that volume is proportional to moles. If we look, we've got 20 centimeters cubed of butane and 200 centimeters cubed of oxygen. One of those has got to be in excess, right? One of those is a limiting reactant. It's a 10-to-1 ratio, but when we look at our stoichiometric ratios, it's 6.5 to 1. So our oxygen is in excess. Now, for oxygen is in excess, that means all of the butane is going to be used, right? So all of the butane is being used. We can use the ratios to think about how much carbon dioxide and how much water is produced. So if 20 centimeters cubed of butane combusted, then we're going to make 4 times as many moles, so 80 centimeters cubed of carbon dioxide, and obviously 100 centimeters cubed of water. If we have used up all of the 20 centimeters cubed of the butane, that means we reacted with 6.5 times as much oxygen, which is 130. So our after is going to be, of the oxygen, is going to be 200 minus the amount of oxygen that reacted, which is 130. So we end up with 70. So these are our volumes at the end of the reaction. Now, if we look at the options, 40 centimeters cubed of carbon dioxide was formed. Nope. 0.065 decimeters cubed of oxygen reacted. Nope. And then 70 centimeters cubed of oxygen remains. Yep. Okay, so there's our answer. So I think an approach in this question is just to try and work it out in the first place and then have a look at what your choices are. Nearly at the end. Okay, so which statement is correct about reactions involving halide ions? Okay, so there's our reactivity series that I was mentioning. I have to think about it. So sodium chloride forms chlorine when added to concentrated sulfuric acid. Well, no. So the chloride ions don't have any reducing power, so they not going to form. They themselves are not going to be oxidized. Sodium chloride forms chlorine when added to bromine. No, because chlorine is more reactive than bromine. So a way to think about it is it's more readily becomes an ion or remains an ion. But bromide would form bromine when it does have a reducing power. It would form that anyway. And then on the last one, what is the percentage yield when 20 grams of aluminium are produced from 50 grams of aluminium oxide? So our mass, MR, moles, MR, mass. So we were told we've got 50 grams of aluminium oxide. We know what its MR is, so we can work out the moles. It's a ratio of 1 to 2, so we know how many moles of aluminium. We know our MR of aluminium, therefore we can work out our mass. And then we were supposed to make 26.47. We in fact made 20, so we had a 75.6% yield. So that finishes a talk through of paper 1. There'll be a separate video on paper 2, but I hope that was useful. But if you have any questions, even having watched this and there's particular questions you want to ask about, then please just get in touch with me. All right, thank you very much.